Hi, so my name is Maxim, and I'm a software engineer / language designer on the Noir team at Aztec. If you're not familiar, Noir is a domain-specific language for snark proving systems. And in this talk, I'm going to be going over how our approach to non-determinism in snarks. So first, I'm going to do a brief intro about Noir, how Noir's architecture is unique and its execution. I'm then going to go over the difference between unconstrained and constrained execution, what that really means, then our specific approach to it and how that applies to Aztec, but also any network that's looking to build something similar to Aztec. So first we have our Noir program, and this is just an example of a classic private transfer circuit where you have a note, commitment, and nullifier, and you want to prove that you have some note in a tree. Noir, this glosses over a lot of what the compiler does, but we're going to convert our source code into abstract circuit intermediate representation. And this is our IR for our circuit language, and it's also going to determine the ABI, which is set by the entry point function. That we have our own IR in between here for our own SSA IR that lets us do a lot of optimizations, but it's not really relevant for at least the circuit level optimizations we're going to be going over today. Then the ABI is going to be filled in by a user who is also the prover, and that's going to create the initial witness. This initial witness is then going to get sent along to the ACVM, the abstract circuit VM. And then finally, we're going to actually send that ACVM to a proving system to construct a proof and verify that proof. To go in a little bit more detail about what constructs a seer, we have mainly just 4 opcodes. There's arithmetic expressions, which is the bulk of what you're going to see in a seer. And this, right now, we just support multivariate quadratic expressions. So we support WIT3, Planckish languages, and R1CS. This could theoretically be expanded to like polynomials of arbitrary degree, but right now it's just quadratic expressions. And then we also have black box functions. These are essentially just proving system optimized functions for very nasty things like Ketchak, SHA, ECDSA. And then we also have a block, our memory block functionality, which enables us to implement dynamic reads and writes in the circuit, and is also going to be implemented on the backend side. And these two are very important for performance, especially in a high-level language like Noir. But the focus of this talk is specifically on non-deterministic computation, which is going to let us actually inject witness information into the witness that isn't necessarily tied to the circuit itself. So I want to think about how, essentially with non-determinism, how does injecting information into the witness, into the circuit, allow us to write our circuit differently and ultimately come to just a more optimized circuit in general. This comes down, we want to basically work with the idea that ZK-DSLs aren't simply like executing programs. We're not taking X plus Y and spitting out Z. We're proving to you we computed that correctly. And that concept allows us to do some neat shortcuts with regards to how we prove certain logic. However, this can get kind of dangerous, and you have to handle it appropriately. So I'm going to walk through a basic example, essentially. So we're going to do a field decomposition. So we start with our simple, like a field of size just 1,000, and we want to convert it into a little endian array of bytes. Here I have some pseudocode naively written of how you could maybe do it in Noir. This is quite inefficient, but we're going to straightforward approach, convert. We're going to convert our field into an integer and perform some bit operations on it. However, yeah, this, at least especially in Noir, is not only expensive, but it's incomplete. We only let you do bit operations on integers as they are range constrained. And so if you had a field that was larger than our largest integer type, you wouldn't even be able to do a byte decomposition using this naive strategy that I just laid out. So we're gonna try a different strategy. We're instead gonna lay down the constraints that I've simplified into this formula, and we're gonna still have as input that field 1000, but now we're gonna do that decomposition we saw on the slide earlier outside the circuit. But if we just have because if we just have this pseudocode on its own, though, it's not clear to the prover exactly how they should be able to do anything. Essentially, the prover does not implicitly know the values of the array. The verifier can understand, this equation, but we need to now, this is where the injecting of the information comes in. We have our field 1000, we step out of the circuit, we decompose it outside the circuit, and we inject that information into the appropriate witness values for the array. And then we have constraints that are now performing multiplications and additions and an ultimate final subtraction against and checking against 0, rather than doing this actually constraining the bit operation itself. So this is the crux of what nondeterminism is and how you can apply it to your circuits to optimize them. And practical ZK applications are always going to require this feature. You're going to need to be able to execute code outside the circuit environment. Noir now supports this in a generalized way through its intermediate representation as Seer, with the introduction of a new opcode. That opcode is Brillig, which will enable Noir developers to now build more powerful applications than they ever were previously able to. So this new opcode Brillig contains code, which is the Brillig intermediate representation, which is executed by an unconstrained finite field virtual machine, the Brillig VM. So you have the AC VM, which when it runs into a Brillig opcode, will execute the Brillig VM, which will be not in an unconstrained environment though. So this is designed to be used as part of an MP complete circuit language, and you technically could integrate Brillig into your MP complete circuit IR if you so chose to. There's other reasons though we wanted to go with Brillig outside of just the nondeterminism example I kind of just went through and purely optimizing circuits. When we were working on Brillig, we wanted to have an emphasis on snark proving efficiency, and also because we wanted to have the ability to attribute incorrectness. And this is because any system that might want to integrate Noir into a true smart contract network like Aztec needs these properties. So what do I mean by attributing incorrectness? If you remember from my first initial compilation overview, we had a user who is also the prover. And in this case, it's fine. They handle their private and public inputs themselves, and they can, if a proof is correct, that means they provided the correct inputs. But now what happens when we separate the user and the prover? And this is what happens if we want, for example, to be able to have proofs over shared public state, where we might have multiple sequencers dealing with public functions. We have two different scenarios that we need to be able to handle. One, when the user provides incorrect inputs, and then we should just have a classic, the function reverts, contract fails. And then we also need to be able to handle when a transaction is valid, but the prover actually incorrectly assigned values, and this leads to a failing proof for something that should be a legitimate transaction. In order to have this attribution of incorrectness, and to ensure that the protocol always has valid proofs of knowledge, we need a virtual machine. And this virtual machine needs to operate as a zero-knowledge circuit, ZKVM. And so the goal of Brillig is to not only be able to just be an unconstrained VM that lets you generalize Noir, but also to be able to use that as a ZKVM for public execution functionality. So to go a little bit into more about what it means to actually execute Brillig, we have it's designed to be as simple as possible. It's a very basic VM. There's only like 15 opcodes, the classic ones you would expect. Not going to list them all, but jump if, load, store. Really not much else. It's register based with a flat memory structure. One of the more interesting features, though, for Brillig is this foreign call opcode. And so this will enable any non-Brillig input to enter the system. So that maybe on its own doesn't make much sense, but I like to look at it as a syscall in C-like architectures. So you're actually interrupting the Brillig program, and the caller of that is going to interpret it and ultimately alter the program's memory and registers. So we actually use this right now in Noir to do our print line functionality, rather than, we could have added another log opcode to our VM. That's also a breaking change. We have to change the serialization. Instead, we can just use this foreign call functionality that we already have. So let's say in the top there, you want to test out your program and see what you're outputting. So I send a print line from my array, and then when I ultimately will go to execute my program, the VM is gonna see the inputs that we have, along with some extra, at least in the case of print line, some type metadata that we've attached to it, and the caller is gonna interpret that like pause information and determine what it should do outside of that. So in the case of print line, we don't have any outputs, but it would also resolve the call outputs if there was a more complex foreign call we were doing. And this is this provided for us a good way to be able to generalize our print functionality without adding anything else to the VM. We were able to just use this kind of syscall and do it. So when you're using Nargo, which is our package manager to execute Noir programs, this is how print line is actually used. But this is really a very simple example, and for more complex programs, it can get a lot more interesting. So Aztec is building a privacy-first layer 2 on Ethereum, and these properties that I just went over about unconstrained execution and the ability to access something outside not only the circuit but from the VM environment itself is necessary for a network like Aztec to exist, because a network like Aztec, which wants to have private functionality and public functionality, you need to be able to execute circuits on the client side, but you also need to have that VM functionality I went over for public sequencers. And you can't do that with just Noir on its own. You need to have Noir that can compile to a seer and can compile to a different IR, such as Brillig, which you can prove an execution trace over. So to just show you a basic example from Aztec, the get secret key functionality is something used throughout the Aztec codebase. The secret key is necessary in order to nullify notes, as Aztec has a UTXO model. And if you look here, we actually there's the get secret key internal, and then we ultimately have to constrain our outputs to make sure we don't have any garbage data. To show you actually what's happening here, this is the use of the oracle again, but this is no longer within the Nargo sphere where you're working locally on your machine. This is within the Aztec execution environment, and it's actually going to be making a call to the Aztec RPC. So you've left the circuit environment completely, and you're actually accessing a database. You're fetching something from that database, which is in this case is the secret key, and you're then going to be operating over it and using it in your circuit. It's also important to note, I said how this stuff needs to be handled very carefully. You have to make sure you can't just fetch unconstrained code, and you can't just fetch things from a database and without writing the appropriate constraints, or else you're potentially gonna circuit could get hacked, and the user themselves using your app could be in danger. This is the simplest example for something in Noir. If I showed you some of the other functionality to read from the Aztec database, it wouldn't fit on one slide or maybe even 2 slides. I highly recommend to dive into the Aztec packages repo if you're curious at all about how this is implemented internally. But otherwise, I would say if you want to get started with Noir, get started with Aztec. Aztec now has a sandbox that integrates this into a new execution environment. Please play around with it, and we're always taking back feedback on how to improve the user experience. I'm happy to take any questions with regards to this talk. Yeah.
Thank you for your great talk. So we have some Q&A time. So do you have any questions?
You showed an example where you do a call to a database using an unconstrained function. Like in Noir, do you have any plans for someone implementing their own kind of these Oracle calls where you can do, like how do you plan to expose this functionality for custom these foreign calls?
Like, so your question is with regards to users being able to implement custom foreign calls?
Yep.
So yeah, foreign calls is definitely most relevant to someone who's going to be making their own execution environment. Like right now, if you want to have something, a foreign call does need to be implemented by whoever is calling the VM. So if you're just working with our classic CLI tool, you are limited to our built-in foreign calls. And then if you're working with Aztec, you're limited to the built-in foreign calls and oracles that Aztec supports. So that's still possible though. It's all open source. You can totally build your own VM and your own caller of the VM that implements its own foreign calls. You could have a foreign call that instead of, I don't know, does some ECDSA functionality. Instead of doing it in Noir, you do it in Rust, or you call a server and do something else. But you can totally do that, and I'm sure there's a big design space for other execution environments surrounding this.
Hey, so as I understand it, the idea is that we're bringing data from outside the circuit into the circuit, right?
Yeah.
And then you have these asserts at the end to just make sure that we don't have crap in there.
Yeah, you don't have garbage.
Yeah, so can we ever have a situation where we have this call goes to some infinite loop and then we're stuck somehow? Could we ever have this sort of situation?
That would be most likely a fault of whoever is implementing the foreign call. Like it would be if whoever is kind of you can so the VM actually, yeah, you're going to pause when you reach a foreign call, and then you need whoever is the caller of the VM, they have to resolve based off those inputs what the output would be. So it wouldn't necessarily be, I guess, infinite loop, but yeah, if whoever implemented that didn't appropriately implement it and they don't ever resolve the call, yeah, the execution could stop theoretically. But if it's correctly implemented, that should never happen. Does that make sense?
Yeah. And if it stops, it doesn't break things, right?
It shouldn't break things. You just, your program never finished. But that's if someone has correctly implemented whatever they're meaning to do, that should not happen. I guess if I don't know, you want to make a server call and you don't appropriately handle, I don't know, the errors returned if that server is down and you just never return that was bugged out, then for example, maybe the person never knows that the circuit should be program ended. But
okay,
yeah.
And are we doing any is this just for the RPC for the nodes, or are we actually calling an API?
No, for this is the RPC that's going to be on the client.
Yeah.
Because this is all for the client side stuff here.
Okay.
Yeah.